You can start, Professor.
We good?
Yes.
Okay. Thank you for coming. And I'll be talking about dispersive techniques in tool calculations, practically for electroweak calculations. And let me start with something that inspired me to start this project on tool calculations. It is actually searching for physics beyond the standard model. So let me start. So generally speaking, we have a three-pronged approach in order to search for physics beyond the standard model. One is effectively direct energy frontier, where you basically collide particles and enough invariant mass, we can use particles and shell beyond standard model physics particles. So this kind of things you can detect basically from Light Scattering Collider. The cosmic frontier is underground space-based telescopes. Yes, mostly neutrino physics. And next one is intensity precision frontier. That is low energy domain, mostly parity violating physics, and with high luminosity beams, it's usually scattering or annihilation production channels. So what I will be concentrating on is parity violation and processes of scattering, what we started a few years ago, basically a decade ago, to study these processes. Then we do scattering of electron beams. So effectively, our host lab is Jefferson Laboratory, where we have electron beam, nice electron beam, and you can choose to scatter electron beams on a target. Could be a proton, that liquid hydrogen, or could be electron. So in case of electron-electron scattering, that would be MOLLER scattering. And of course, in terms of scattering processes, you would have photon exchange, neutral current, Z-boson, or if there is some beyond standard model physics carrier, that's going to be parity violating Z prime, for instance, weakly coupled new particle. Okay, so that's a key point here, is to start to study, to search for physics beyond the standard model for virtual particles, because then at the point when universe falls, so these particles no more on shells, so they're actually interaction carriers. We can distinguish two types of beyond standard model new particles, let's say like that. It would be dark photon, so it's parity conserving, massive and weakly coupled, and it would be, of course, parity violating, so that would be Z prime. So in order to search for these things, you need to do very precision measurements of observables in these scattering processes. To start with, you need to get uncertainty on winded mixing angle square less than 0.5%. And you go away from the Z resonance, so it is in a low momentum transfer regime. So what we get from this is neutrino scattering, new physics, electromagnetic interference, weak electromagnetic interference, and it comes with atomic parity violation, so the parity transition in heavy atoms, and parity violating electron scattering. And this is what we started to learn about. And effectively, you look at polarized scattering, electrons on a target, and electron could be right-handed or left-handed, it's longitudinally polarized. And of course, since the interaction is parity violating, Z exchange, there's a left and right-handed coupling constants are different, so you can construct this asymmetry observable, which is simply speaking difference between cross sections left and right-handed, normalized by left plus right-handed. So whatever is parity conserving will cancel out of the numerator of asymmetry, and what will be left with is only parity violating terms, which are manifesting themselves in terms of interference terms, parity conserving, matrix element, photon exchange, Z-boson, gamma new physics. In case of that, it's a Z prime, so it's a parity violating, or Z-boson exchange with the new physics. It could be either parity violating or parity conserving, like dark photon. Now, at effective scale, so to speak, we start to understand what kind of energy scales we are probing. So you construct, well, effectively based on full fermion interaction, Fermi theory, basically. So let's say you look at the electron-proton scattering, and what you would have is that is parity violating standard model representation. This is a new physics representation. So you have obviously electron current, the quark current, and electron scatters on the proton. So you have Fermi constant here. And for new physics, you kind of absorb the same kind of terminology so to beyond the standard model. So you have a mass scale, the coupling constant, representative to, well, it's not the Fermi constant, but again, electron current and quark currents combined over quarks in proton, and with this kind of effective coefficients, which we don't know, basically. But if we combine these two Lagrangian densities, one can look at this, what these structure constants in a quark current in a standard model representation. So this coefficient forms here. And if you recall, what the deep charge of the proton is combination of twice the structure constant for up quark plus structure constant for down quark with this -2 coefficient in front. This combination of two actually gives us an idea what this is nothing else but kind of uncertainty which we put on a big charge of a proton, which is related if the new physics is hidden inside this uncertainty. So that is what we actually can get as an extract a scale of new physics. If we just basically take uncertainty on charge of the proton around 6%, the scale of the new physics which you are probing is around 3.7 teraelectron. So lots of experiments were dedicated to this idea of searching for new physics, and of course the asymmetries were measured on the different targets, meaning protons and electrons, but most of them completed. QVIC was a recent JLab report where they reported no deviation from the standard model.
Your young standard model. You're thinking about the difference or Fermi interaction. What?
No, for MOLLER? No, it's just how to do standard model calculations, right? So
what is the thinking of what your theory that you're thinking about beyond the standard?
It's there is no, I mean, either U1 prime extension.
What you were thinking of your or Fermi interaction.
It's just effective. It's just effective, right? So it's just basically getting the idea of the scale of that physics, what kind of probing at this time. Well, doesn't matter. I mean, all these theories in this H constant, basically, it's effective theory. So the two new experiments which are coming with MOLLER and P2, one is in JLab, another one in Mainz and Göttingen University. So they claim put uncertainty on the Weinberg mixing temples for less than 0.002, which is actually around 7 GeV scale, which you can do on new physics. So obviously, one, if measured with such a precision, needs to push frontiers of calculation precision. So it's literally what you need to do. Let's say if you concentrate on MOLLER, so it's electron-electron scattering in T channel, U channel, you have these two processes at 3 levels, simplistic, of course. And if you construct this asymmetry, left-right asymmetry between electron polarized and time left-right, well, it is very simple expression which is proportional to a 3-level definition of weak charge of electron. And since the sine square Weinberg angle is around 0.25 with 2/4, something like that, let's see, this is very sensitive to asymmetry, is very sensitive correlation to sine square W. One, of course, cannot just be sufficient with just a 3-level calculation, because as already work was done, starting with Czarnecki, Marciano, and then Pizzarini. So these guys did MS bar calculations on shell. We did on shell as well. But we did full Electroweak set of 1 loop graphs. And we found obviously everybody found that the next leading order contribution is substantial. So although of course perturbation expansion in electroweak calculations is converging, but not that convergent very strongly. So if you look at the beyond the leading order, so effectively you get down two matrix elements, 3 level and 1 loop, you square it by absolute value, so you get these orders of alpha expansion, and obviously this interference time between 3 level and 1 loop is order of alpha cube, but also there is the next to the leading that is going to be alpha to the 4, which is basically reducible 2 loop calculations, and of course one has to add 2 loop calculations, irreducible in electroweak calculations. So we done this, of course, very detailed analyzing this particular contribution. We done this quadratic, and we done some of the contributions from the 2 loop. Let's consider leading contributions from the 2 loop and electroweak asymmetries. So what we have found, if you look at the correction on asymmetry, so let's say corrected asymmetry minus 3 level asymmetry divided by 3 level, so it's basically relative correction. So one can split it up in QED and in weak correction. So QED is primarily correction to denominator of asymmetry, and the weak correction is actually depends on the center of mass energy. So we consider many kind of points. So this is where Muller proposed Muller experiment, P multiple point for center of mass energy at 90 degrees in the center of mass scattering angle. So we can see that correction next to leading order can reach 60%, which is, perturbatively speaking, it's humongous. So, and if you look at the precision of experiment, one would have to obviously go beyond 1 loop calculations in order to squeeze this theoretical uncertainty to the sub-percent level. So that was kind of interesting. So, and calculations were done in unshelled approach. So we started to look, 5 years ago, roughly at the next leading order. And first is obviously the quadratic, which is basically 1 loop squared. And second one is irreducible 2 loop multiplied by 3 level. So we've done all of the graphs contributing to the quadratic correction to alpha to the 4 and leading order to 2 loop literal calculations. So of course, alpha to the 4 contribution is already suppressed by 1 over of alpha, and of course there is a convergence, so preserving convergence. So that's a leading order symmetry as a function of a scattering angle in center of mass reference frame. And so if we look at the leading plus 1 loop plus quadratic, so that is green, and leading plus NLO is 1 loop basically plus leading order. So that is a shift due to the alpha to the 4 contribution. So it's already much better convergence, of course. So one can look at the full 2 loop calculations for electroweak, but it's a very massive job because, and this is something what is in progress. This requires a lot of computational power. And of course, we need to look at the 2 loop graphs, which will have photons, WZ, Higgs, everything. All the standard model have been stored, every single packet. So masses are propagated different. So couplings, momentum dependent in some cases. And so this is very massive job to do 2 loop calculations in electroweak physics. Okay, so we found, just numerically speaking, what was shift from NLO to taking 2 loop, leading and quadratic is roughly 4%, which is already very big win in order to squeeze the theoretical uncertainty for the Muller. Okay, so here it is. Now that was an introduction, the inspiration. Why do we do 2 loop calculations effectively for Muller or electron-proton scattering? Well, first of all, of course, one has to, cross-check these results, get something interestingly what we have developed, what we can do dispersive representation of two-loop calculations with Pasarino-Weltman functions. So it's Pasarino-Weltman basis. So cross-check with previous work, and effectively with Pasarino-Weltman basis, we have lots of packages already developed. So using these functions, so we can run full two-loop calculations. Yeah, sure. Yes.
Higher order, so we have the loop and the terminal, you can also do quarks, right?
Well, yes, in the vacuum polarization, let's say P2 bar pairs. Yes.
And then the blue ones inside too?
No, this is the okay. Good question. It's relevant to atomic vacuum polarization, as we call it, right? So we basically flexibly fix the mass of the core to a ratio, the E plus and minus go to hadrons, normalize E plus and minus goes to E plus and minus. So we just basically fit and extrapolate to low center of mass and this is how we done. It's kind of common approach, and I understand when you have quarks in the loop, so loop with gluons, but we cannot push into this kind of domain like that.
An expansion.
Oh yeah, absolutely. Alpha X, exactly. So effectively, our quark masses in the vacuum polarization in the bubbles that people pair, we do have effective masses of gluons. Okay, so what is an idea here with dispersive subloop insertion? Idea is following. So let's say we start with something very, simple topologies. So what is written here, subloop insertion self-energy. So let's say we have this kind of 2, 3, and 4 multiplicity type 2-loop graphs with self-energy insertions. On these lines, which we see, it could be fermions, vector bosons, ZWs, whatnot, right? So we generalize as much as possible. So idea is to use this loop, subloop, as an insertion which can be dispersively represented. This idea already been some time ago on the market, but what we did, we generalized that and we made not only for self-energy insertions, but triangle and boxes insertions as well. So we push this, much forward, right? So, and that's going to be rest of the seminar about. So what did we do? Okay, so, but what is an advantage? Okay, so if you have this self-energy insertion and make this self-energy insertion in this dispersive representation, so there's basically threshold and some Kashif area, effectively, right? So this is the imaginary part of 2-point function. There's going to be 2 points.
What do you see?
It's based on the Kashif area. I'm sorry?
What theory are you studying here?
Electroweak standard model.
So this thermal light, the internal thing?
Fermion, vector boson, you name it, it's just general. Yeah, but then later, when you have a framework, you put specific particles in this approach. I will speak about it for sure. Right? So,
and these are part of randomization. Again, you are going to randomize your.
Of course, and we usually use unshelled
on the vertex or
yes. And that's what I will speak about, right? So in the normalization, of course, part of the representation, you can choose MS bar, subtraction, or unshelled. So this again, it's a general approach. Okay, but instead of having basically irrational functions with Q square here is momentum which is running in the second loop. What you can do instead of this 2-point function, you can replace this with discontinuity of 2-point function and divide it by this s minus 2 squared, shifted to complex plane, of course. So, but thing is, this is function of s. This is basically some parameter of dispersive integration. It doesn't do anything with the second loop integration. An entire insertion is compactified into the propagator structure. Propagator-like structure, the momentum Q square over second loop momentum, S is basically effectively somewhat the mass square of that property. Okay, now then you have, instead of this insertion propagator-like structure with dispersive integration, now second loop integration is nothing else but one loop calculation with additional propagator. That's basically idea. Now going to details. Okay, here we go. So we start, of course, we could have vector bosons, so basically different mixings, W, W, gamma, 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 C, stuff like that. And we can fermion, self-energy, insertion. So of course, in case of vector boson, general Lorentz structure, so with transverse contribution will be two contributions. And for fermion, since we're working in the generalized approach, so it could be left and right-handed parts of insertion and scalar, so the general representation of that insertion, and omega minus, omega plus, is chirality projection, so left and right-handed side on this. Okay, so what you can do next is, generally speaking, if you can renormalize subloop insertion, usually subtractions. Well, in unshelled, subtraction will be on mass shell. So I just want to show different scale, whatever scale, we just do subtractions for this self-energy graphs, and you subtract a certain scale minus derivative times Q square minus M. That will treat UV divergence out. So UV divergence is out. But if you represent every single 2-point function insertion, if in case of dispersive representation, so this maps to this to this, and derivative maps to this, do the subtractions like this, so you consider now so-called multiply subtracted dispersive insertion. The importance of this multiply subtracted dispersive insertion is a matter of fact that this integral is convergent. That's very important because its behavior is supposed to be stronger than 1 over S squared. Otherwise, it blows up. So this is why you do renormalization of subloop, form so-called multiply subtracted dispersive insertions, and then you can carry on into the second loop integration. Now, if you look at the more specific mixings in the self-energy insertion, like Z, Z, W, W, now we use unshell renormalization. It's a standard process to do renormalization of these insertions. So you form these multiply subtracted dispersive representations. Again, everything with function of S doesn't do anything for second loop integration. So you can just carry it out as a constant. And what you left with is simple propagator structure. Also for gamma Z mixing and gamma gamma mixing. Matter of fact, these conditions in front which will show up will cancel certain degree of propagators in the second loop. So it will make things a little bit easier. And so for fermion insertions, that's a general structure of fermion insertion and renormalization of fermion self-energy, electron self-energy. So one can write this in subtracted dispersive representation. This is coefficients due to the fact of this renormalization procedure. But again, bottom line, there's some propagator, like structure in numerator will cancel 1 degree of propagator in the second loop, and what is carried into the second loop integration, this kind of propagator, and that's it. That is your kind of structure which goes into that second loop integration. And here we are. So one can form, this is what we did, just generalize with effective propagators for self-energy. So vector boson to vector boson. So different types of insertions you can consider. Self-energy inserted to different topologies, to self-energy triangle into the box. So instead of these kind of shaded lines, you can form these propagators that these coefficients in front were just functions of S parameter, and these imaginary parts of 2-point functions also functions of S parameter, so it doesn't do anything for second loop integration. And what goes into the second loop is basically these two structures, which is quite easy to couple, generally speaking. Same for fermion, a little bit more complicated for fermion self-energy insertion, right? But again, it doesn't matter. We still have somewhat very simplistic propagator type structure, which is pushed towards the second loop integration. Okay, now that was a story about when we were able to renormalize subloops. So we had these subtractions. So by means unsharing normalization or MS bar. Let's be useful. But more generally, if we want to generalize it as much as possible, we need to keep dimensionally regularized insertion analytically intact. And then whatever you want to do with this, if dimensionally regularized two-loop result, you can apply a normalization of UI. So, but in order to formalize dimensional regularization for insertions in these two-loop calculations, we start with something simple. B function, it's a two-point function, it's a Pasadena development function, basically, it's a self-energy, scalar and vector coefficient and tensor coefficient function. It has well-known analytical representation. 3-point functions, 4-point functions, and so on, high multiplicity. We have only for particular cases analytical representation. But for 2-point functions, we know analytical structure quite well. And so since these self-energy insertions, they are functions of these 2-point functions, if we can represent this dispersively with inclusion of dimensional regularization intact, because if you do subtractions, 1 over epsilon poles disappear because they will renormalize. So, but here you want to keep it, and this is what we do. So first of all, we take 2-point function and separate it to one is going to be UV divergent part, basically just the 1 over epsilon poles, and the final part. Okay, if we do this, UV divergent part has very simple structure. So that's 1 over epsilon pole, where epsilon is basically 4 minus d over 2, right? So with constants, log with mass scale mu, dimensional regularization parameter mass scale mu, and some coefficients which are functions of m1 and 2, and this is polynomial term in momenta. But this momenta could be momenta of the second loop integral. So okay, but it's polynomial. It's just basically going to introduce you new degrees in numerator algebra, but it doesn't make your calculations of two-loop graph complicated. So you can do this on paper. Now the final part, this is what it is. Now, if you want to keep this epsilon term analytically, we have to keep this expansion up to linear epsilon term, because second loop will have 1 over epsilon, and multiplied by epsilon from insertion will result in the final term. So we need to keep that epsilon linear terms. Okay, so that looks kind of complicated, but still it is possible to shuffle this into dispersive propagator-like structure representation. Here we go. Now, first of all, you might just think, okay, I can take final part of this 2-point function and dispersively represent like this. That is not going to work. I should cross it like that because it is divergent integral, basically, because it behaves something like 1 over s. So that's why we did originally sub-loop renormalization, and that gave us possibility to form these multiply subtracted dispersive insertions which are convergent. Aha, but this one is not. So what did we do? We took this finite part and recall how did we do renormalization. Basically, the renormalization was done subtraction at some mass scale minus derivative on that mass scale multiplied by p squared minus lambda squared. So we just basically did everything up to, I mean, depends on the rank of this 2-point function because it's not a scalar theory anymore. Taylor expansion around some parameter lambda squared. This is generally speaking just a constant, just a lambda could be numeric value arbitrary. So we do subtract this from finite part and add exactly the same. It's a key point. So we did nothing, but for the finite part subtracted with these terms, we can form multiply subtracted dispersive insertions. And this is what is in the red. It is convergent dispersive integral. Now, what is left is this plus part, finite part, but this is just a constant, as I said. P squared is equal to lambda squared, multiplied by p squared minus lambda squared to the power I. So, but that will also just basically contribute to the numerator algebra of the second proof. And effectively, we can use Poisson-Bergman basis for two-loop calculations and automatize this to the full-loop calculations, full two-loop calculations. Here we go. Now, two-point function as a self-energy, it's a self-energy basically, is and does have very interesting analytical structure. So we have this 1 over epsilon poles. We have these contributions. All of these are polynomial in momentum of the second. And dispersive term has already subtracted structure and already well-behaved integral, and just gives us second loop integral supplied with additional property. That's it. And now what you need to do is, of course, to generalize. If you take, well, let's say vector boson insertion, generally it's a second rank tensor. So you comprise this dispersive insertion. Let's say only dispersive part only, just to show you how generalization works. And as you go into the second loop integral, you get this kind of integration, which is for fermions also, left, right structure, only additional property. When it goes into the second loop, again, just additional property. There's of course a bunch of propagators from the second loop topology, depends on the multiplicity of the second loop. And that can be done. As a result, your two-loop result with self-energy insertion, what you have is effectively two types of discontinuities, transverse and longitudinal, for self-energy vector boson insertion. In front of these coefficients from two-loop integration in terms of 2, 3-point, 4-point functions, because second loop integral could have 5 multiplicities, of course, not only B, C, D, E, whatnot, right? And you just need to do what integrate numeric scalar integral of dispersive parameter S. And that's it. That's your two-loop result. Now, for fermions, the same, but only what you have left and right-handed contribution and scalar contribution. And that is a self-energy what Oleg did some times ago. We generalized for any Electroweak self-energy insertion into the self-energy, into triangle, and to box contributions. Now, okay. So now this is genuinely yes, please go ahead.
I was wondering, so the photons and the particles without mass, do you run into trouble with that infrared?
Yes, very good question. We regularize infrared derivatives by giving photon and mass, and then deal it with, for starters, with soft quantum trouble, initial final sequence. Yeah, good question. Now let's see if we would like to put triangle as an insertion into the second loop. This is the idea. So first of all, 3-point function does not have for any general analytical structure. So it's only for particular cases. Some masses are equal, one mass is 0, yada yada. So, but if you just say, okay, all the masses are different, that's it. So that's a definition of 3-point function. Okay, so this is in d dimensions, so of course it's a convergent, and just 4-dimensional. So idea what we have came up is to reduce 3-point function to scalar integral representation of 2-point function, which we know how to deal with, because we know how to represent 2-point function dispersively, because it has very nice analytical structures. So what did we do? So take 3-point functions. So let's say it's a scalar, of course. Numerical algebra is just one. So 3 propagators based on this graph. what we do, let's say we think, okay, P2 momenta of a second loop. Now we join propagators of two propagators with some momenta P1, so maybe it's some shell or not, but it's not a moment of the second loop. You can always find this way. And while doing Feynman trick, we can join these two propagators together. So what you get this Feynman integral, of course, the Feynman parameter, and we have this quadratic form. Okay, and with this squared effective mass, which is that structure effectively. X bar is 1 minus x, but x is Feynman parameter. Now, of course, it does not look like a two-point function quite yet, but well-known through mass differentiation. So we did simple thing. We took and removed this quadratic form in three-point function representation by just basically shifting the squared mass by some mass shift parameter lambda, taking the derivative, removing square. Now this is only first order, and putting things back to three-point function. What I see, it is two-point function with following arguments, which you need to differentiate with mass shift parameter and integrate over Feynman parameter. But for two-point function, I know everything how to do dispersive representation. Now, key point here might ask, if you do numerical integration, that's fine, it could be done. But numerical differentiation could be tricky. So what we do, we can do it analytically because we do know these functions, analytical structure, we can do it analytically in mathematics very easy. Differentiation with mass shift parameters, so there is no something like numerical differentiation is needed. Okay, but I will keep it just like that. Okay, so diagrammatically speaking, triangle insertion will be replaced by self-energy insertion with following masses, the following momenta coming into that self-energy, but of course you need to differentiate it and integrate it over Feynman parameter. And one thing, of course, the theory is not a scalar, so we will have numerator algebra, and we will have three-point functions of arbitrary tensorial structure. But you need to do map of tensors of three-point functions on the tensors of two-point functions. And let me show you how to do this. We use, of course, standard tensor decomposition technique. This is coming from Pasarina Veltman paper, quite classical, old 1979. And idea here is, let's say, if I have this three-point function with a higher order numerator algebra, so it's a vector, let's say. What I do on the left-hand side, I do tensor decomposition and use two-point representation of three-point function. I do tensor decomposition for two-point function on the right-hand side under this integral. Then match coefficients in front of P1 and P2, I get this mapping between higher order tensor coefficient three-point functions like C1, C2 to two-point functions, for which again I know how to put dispersive representation. So immediately every three-point function of arbitrary tensorial rank can be written as this two-point function representation like this, the coefficients like that here, and of course you need to have the derivative and final integral and integrate it. So we can do it for four-point functions. We did it for paper, of course, and PRD. So, and for five-point functions, also done already. So, no, because you see, it's not a scalar theory. Yeah. It's a numerator algebra. So, well, numerical case I will show you as an example for scalar theory.
From war identity for something related to something. Long war identity.
Well,
the game theory.
I see, I'm sorry.
In the game theory, you can relate.
Well, possibly, but that's what
war identity.
Yeah, okay, but word identity is mostly you can constrain your minimization constants effectively when you do minimization process. So Okay, but what we have, yeah, okay, we have this 3-point functions of arbitrary rank is a 3-point function coefficients. Now we have 2-point functions, and one can surely do dispersive insertion of 3-point functions. Okay, so that kind of topology you would see just for multiplicity 2, 3, and 4 is just an example, of course. There are more topologies for a process like this, and that's just representation. So what will happen if you insert 3-point function here, here, and here? So that is going to be effectively these gray blobs replaced by some sort of effective propagator with a mass S. So specifically to two-loop calculations, so if I have 3-point function insertion, like scalar, for example, we join two propagators. Now, for this specific case, Q2 is momenta running in second loop, so we don't want to have two propagators joined where you have momenta of the second loop because it's going to mess up. Okay? So just join the propagators for loop insertion momenta and external momenta and masses. Do a final trick, mass shift differentiation, and that's what your insertion is going to look like. This effective mass square, and insertion, of course, has a structure of propagator in a second loop. We did test all the 3-point functions, this kind of dispersive representation in 2-point function basis. And that's what we see here with the yellow curve. It is a polar package, also loop tools, and different 3-point function coefficients, 0, 1, 2, and well, it just as an example. And the blue dots is what dispersive integration gives us. So that's kind of boost of confidence. We have 3-point functions represented dispersively through 2-point functions. And now replace insertion with simple propagator. In terms of regularization, C0 of course is UV finite, but if you look at the C00 functions, so second rank tensor already being considered, you need this regularization, dimensional regularization, and one can exactly basically propagate the idea what we've done with 2-point function with dimensional regularization, dispersive representation, and that's what you get. Of course, formula is big, but matter of fact, it's not. It's just basically general expression for every run, for anything, masses are all different. So, and again, this is going to be just a polynomial term which goes to the second loop integral, and it's doable, it's just a numerator algebra. And last term, that is a dispersive insertion with, again, just a propagator going into the second loop. Okay, one more thing. With these 3-point functions, there is one kind of little problem, but we overcome this problem quite interestingly. So, first of all, if you look at the 3-point function representation on 2-point function basis and use 2-point function basis dispersive representation, there is a possibility when this effective mass square could become negative. So it's going to be case of imaginary mass. So that basically just make things different for representation of 2-point function dispersively. There is no branch point anymore because you have imaginary mass in a 2-point function. So it's just basically integral from minus infinity to plus infinity. You make things of some lambda, big number, square to lambda square. And it does converge quite well, and it just not discontinuity, do the contour integration, just a 2-point function divided by this s minus p squared. Again, just a plain contribution, application of Cauchy theorem. So we also, of course, compared results which we have from this dispersive representation with imaginary masses, and cuts off. There's more numbers here, but and loop tools results, and you can see very much, 1 to 1. So that needed to be covered because that momenta P1 squared could be space-like or could be time-like. And if it's time-like and large enough, this guy could become negative than 1 to squared. So that needed to be addressed. So I would like to come to kind of numerical example to show you how does it work from the beginning to the end. But for scalar field, because again, it's otherwise takes a little bit more space in terms of show. So let's say this is classical two-loop irreducible graph. Momentum P incoming, so the momentum of one loop Q1, momentum of second loop Q2. Consider all the masses are different. That's it. So if you write this two-loop integral, so of course you have this bunch of propagators coming from here, 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 and here, and you identify what good part. It's up to you basically, but I choose to identify this part will be triangle insertion. So I choose this is triangle contribution. So I choose, of course, to join propagators where second loop momentum is not present. So these two. And form from two 3-point functions, 2-point functions. So that's what I get as a result of this integral. So of course we will do discontinuities of 2-point function, derivative with mass shift, integration of course with Feynman parameter, and this R function depends on what kind of mass M1, 2 squared you're gonna have. This is step function which basically change this integral from threshold to minus infinity plus infinity, depends on what M1, 2 squared is, positive or negative. So this is basically a two-loop insertion into the second loop. And now you have again 3 propagators left, one only dispersive propagator. It would be 3-point function. It's going to be scalar 3-point function. But we also can represent the scalar 3-point function as 2-point function. And as a result, for second 3-point function, we have another mass shift parameter psi, for instance. You need only scalar integration. This is analytically differentiated. You have 2 mass shift parameters, 1, 2, 4, 5, and that's it. That's all the formula you would have for two-loop calculations of a graph like that. It's a key point because when we look at the Electroweak two-loop calculations for full two-loop calculations for MOLLER, we're speaking about thousands and tens of thousands diagrams. So you need compact analytical structure in order to evaluate this enormous number of graphs. And if you compare this to Berger and Bohm paper, they have lots of formulas based, of course, to derive this exactly the same graph compared to what we have. Is well, just a scalar integration. So this is for comparison purposes. Of course, just one has to do some numbers and compare. Otherwise, it's just math. So this momentum coming into this graph, space like time like, of course, above threshold we have of course imaginary part acquired by this self-energy graph. So this is a Berger and Bohm results from quite some time ago. So, and we can just compare the numbers from what they have and what we have. That's it. Thank you.
Thank you very much. Question from the audience?
Imaginary masses. Your diagram has a path.
Yeah, but the goal is in complex way, not in the real, not the branch point, not in the real access. So, and which is basically the contour over half of the upper part of the complex plane. You don't need to do this kind of contour like this, so you need to do Schwarz reflection principle.
Yeah, but what does it mean physically?
It's not mathematical. It's mathematical, very mathematical. It is effective math. It's coming from joining using finite properties. So one might characterize about physical meaning of that particular math, but I don't know any specific physical attachment.
Because it is caused by some square momentum that becomes possibly go negative. So
Well,
so
yeah.
that's not physical meaning.
Well, the momentum becomes where was it? Somewhere. The momentum becomes tedious timeline, so positive, right? So
Right.
yeah. So that could overcome, of course, if it's a slow masses, it will become.
It must have some physical.
I'm saying,
But that's also something called, I don't know, threshold. or something.
yeah, perhaps yes, it is. We encountered this and started thinking what we can do, and basically come up with solution. Basically, simple, just over half plane of integration. That's pretty much all.
Good question? Good.
Yeah, we keep about it. Again, I couldn't quite hear the name, so, yes. You mean, gamma mix to bar and photon? Yes. Yeah. We just give we want to take part mass from what we want. That is inevitably produced to solar rays. If we move these next to the medium over to this parameterization of this R ratio, that's going to be much more time. But and it will of course probably still but polarization, that will then that will people bar the foot goes. Okay, so combine two of course start to stick to a bar parameter. So that needs to be done always, but we didn't do this. That's a valid approach. So we just cut this and assuming what small variation of fixed mass towards work masses is not going to impact dramatically. So but it is part of uncertainty. I mean, yeah, but it is not trivial again to do the speeds with two loops included. But yeah,
What was it from the audience? This guy, see the question, you said, final presentation.
let's say in front.
You said, for example, you said, final presentation.
Final parameter.
And not finger. What?
Not
Finger presentation.
finger parameter. No, let's.
You think that the same person?
No. No, it's just our school. I mean, it's one. It's finding permit is quite, yeah. Something that is neat. It's math, right?
What was it from the audience?
No, it's not a consideration before. Taking a series.
No, generalization considered for any field. Yeah, exactly. But exactly. There is exactly. Exactly. But first you do computation. This is why we did the dimensional regularization. You keeping one of the excellent poles intact. So we first compute this analytically to result. And then we come to the point of renormalization and application of port identities in order to constrain number of independent renormalization constants and derive normalization constants renormalization condition. Yeah, but it's yes, but again, it's not in this case. It's related to dispersive. No, I would say it's not a scalar theory. No.
You don't have any numerator there.
Yes, of course. Yeah, here it is. We start
Now we're going there, but the other one, you got to
well, just an example, to make an example, of course.
your example is very simple.
No, examples is scalar theory, of course, just to show what the
I don't know how we can, so when it means you were showing explicitly saying how do you deal with the denominators, because the denominators it will show you how many internal probabilities you have. And whatever is in the numerator should also be there, of course.
Yes, of course. But again, if I show you an example with, let's say QED or, I mean, it's going to take 15 more slides. If we have the director structure, right? So it's done. I mean, my student is finishing his PhD on doing this based on this all the numerator algebra included, but it's a easy thesis.
Showing you the point is how you treat this product of denominator. That's it.
Yeah. And for numerator algebra, we use potential comparison. There is bunch, I mean, mapping theories, how all these people functions can be given. It's not based on a word identities. It's just
No, it's not based on here where we have
exactly, but
I think this probably is possible to be done also. But what I think it's doing is reducing the number of factors in the denominator using some kind of relation to integrals that has fewer factors in the denominator. And you call that a two-point function if you want, but actually it's a mathematical expression that has fewer factors in the denominator. That's it.
no, it's
Well, it will be there. But you are making a reduction of the denominator in terms of how many factors you have.
What questions with W's? Zoom people have questions.
And the people in Zoom, do you have questions? People in Zoom?
I think we'll have
No, maybe they're.
but I don't see the questions.
I will provide them. Questions?
Yeah, but
Questions?
yeah, exactly.
It's just a mathematical treatment of the denominator. That's it. maybe it's not a good language to say that we reduce it to 2-point functions, because we cannot reduce it to 2-point functions. But what do you do with the other point? A 2-point function has a 3-point function has 3 external legs.
So you have to be the same, that is where I'm interpretation. So you need to, this is another degree of freedom. When we squeeze 3 to 2, of course, you produce another device that's freedom. Just replacement by scalar and the ground.
Good comment. People in Zoom, we have questions, so we'll send the speaker again to the next talk.